Welcome to the Winds and Currents webinar. Today's speaker is Hervé Giordani from Meteo France, who is going to present on possibilities for a Winds and Currents mission. So the format will be that we'll have about comparatively short talk and ample time for discussion. So please pull your questions together so that we can have a lively discussion afterwards. And are you ready, Hervé?
Okay. So can you see the slides?
Looks great.
Okay. So good morning, everyone. I'm Hervé Giordani, and I'm working in the research department of Meteo France, and more precisely in the climate group of the National Center of Meteorological Research. So I'm going to present you some results on the ocean and atmospheric boundary layer dynamics, and which shows the need to have a measurement of surface current and surface wind. So I focused on the tropical Atlantic because usually the climate models usually fail in simulating realistic cold tongue and monsoon onset. You see on this figure, on the bottom figure, the cold tongue, which developed in July 2006, which was the period, the year of the AMA experiment, where we had data. So when looking at the SST and surface current animation, you see a very high spatial temporal variability, which is associated with the westward propagation of the tropical instability waves. And you see the equatorial cooling is not monotonic, but highly intermittent. And this intermittent cooling is due to the vertical mixing in the boundary layer, in the oceanic boundary layer. And this mixing is very active just south of the equator and in the tropical instability waves. So at the seasonal scale, you see the presence on the top figure of the equatorial cold tongue and the vertical mixing in the middle figure. But this cold tongue is not correlated with the wind stress, because the high intensity of the wind stress are far south in the southern hemisphere. So at the intraseasonal scale, so the top left figure shows present the turbulent mixing at 10 west and between 10 south and 4 north, and you see that the maxima of vertical mixing are confined in the equatorial belt, while the surface wind stress on the right, the top right figure, has its maxima far south in the southern hemisphere. So it's difficult to consider the surface wind stress as the most relevant forcing for vertical mixing. So on the bottom left figure, we have the Hofmüller diagram of the wind energy flux. So the wind energy flux is the sources of the kinetic energy provided by the atmosphere to the ocean. This is the forcing of the kinetic energy equation. And it is also the wind work at the ocean surface. And it is expressed as a scalar product between the surface wind stress and the surface current. And unlike the surface wind stress, you see that the wave is located at its maxima intensity located in the equatorial band. So the wave is better explains the intra-seasonal variability of the vertical mixing than the surface wind stress. So, but the question is now is how the wave control the vertical mixing and finally the cooling. So on the left figure, you see the vertical velocity. And once again, you see that the greatest intensity are located in the equatorial belt and the equatorial band. And the frequency of the signal is close to the wave one. So we conclude that the wave is also a leading forcing for vertical motion. And associated with the alternance of this upward motion and downward motion, you see on the right figure that the mixed layer depth shallow for upward motion and deepened for downward motion. So coupled to this mixed layer depth variation, the stratification on the left and the vertical shear of the horizontal current at the mixed layer base tend to increase for upward motion and decrease for downward motion. So based on this analysis, I can propose you the following mechanisms which control the cooling by mixing. So the wind energy flux excites the vertical velocity, which adjusts the mixed layer depth, its stratification, and the vertical shear on the mixed layer. And these parameters are key parameters in the production in turbulent kinetic energy, and finally in the cooling by turbulent mixing. So we go back at seasonal scale, and on the top figure we see that the shallowest MLD in blue color are collocated with the equatorial upwelling in purple line. This corresponds to the mixed layer depth adjustment by the vertical velocity. And in the bottom figure, you see that the maximum of turbulent mixing bounded by the blue line is collocated with shallow MLD in blue, in grid line, and intense wind energy flux. So the mechanisms which link the wind energy flux to the vertical mixing and finally to the cooling is also valid at seasonal scale. So now the question is this mechanism valid at climate scale? So in the climate model of CNRM, we classified the cold tongue into two categories, the intense cold tongue and the weak cold tongue. So I focused here in the intense cold tongue on the left figure, and this is the intense cold tongue were characterized by a negative anomaly in the vertical mixing. And on the Soft-Muller diagram, you see that the negative anomalies in vertical mixing in blue color are collocated with positive anomaly of wave in the black line and negative anomalies in mixed layer depth. So also at climate scale, the scheme which is wave controls the vertical velocity and adjusts the mixed layer depth and its property, also the turbulent kinetic energy, and finally the mixing and the cooling is also valid at climate scales. So now I would like to show you, to tell some more about the coupling between the cold tongue and the equatorial front with the atmosphere. So on the top figure, we have the Hervé diagram of SST across the equator, and you see that before June, so before the monsoon onset, the wind increased from the southern hemisphere up to the equator, as you can see on the bottom figure. But after June, so after the cold tongue onset, the wind decreases above the cold tongue and increases again above the SST gradient associated with the equatorial front. So this strong coupling between the equatorial front and with the surface wind has motivated to study the processes which control the frontogenesis in the equatorial front. So on the top figure, you see the equatorial front, which is materialized by the purple line, and the color is a frontogenetic function which produces the frontogenesis in the equatorial front. And this frontogenetic function, which is written here, represents the deformation field of the temperature by the horizontal current. You see that the frontogenetic function has two components: a zonal component, which is frontogenetic in the middle of the basin, in the center of the basin, and correspond to the interaction between the south equatorial current and the eddies associated with the tropical instability waves, which travel westward in the basin. And the meridional current is frontogenetic in the eastern part of the basin and correspond to the convergence between the south equatorial current and the Guinea current. So the meridional component prevails over the zonal component in the total frontogenesis function. So in order to estimate the role of the surface wind in frontogenesis, the Hofmüller diagram on the top left figure shows the superimposition of the surface wind stress in color with wind energy flux in black line. And you see that unlike the surface wind stress, the wind energy flux better explains the biweekly frequency in the convergence of the meridional current on the left bottom figure, and also in the frontogenesis materialized by the purple line. So in fact, the biweekly intermittency of frontogenesis reflects the convergence pulses between the south equatorial current and the Guinea current induced by the wind energy flux. So, and finally, on the on the right bottom figure, you see a vertical section across the equator, which superimposes the circulation and the temperature. And you can see that the convergence of the cross-equatorial cell tend to increase the temperature gradient in upper layers. So based on this result, I propose you the conceptual scheme of frontogenesis in the equatorial front. So the wind energy flux on the left control for the south equatorial current and the Guinea current, and also the vertical velocity, which adjusts the mixed layer depth, controls the turbulent kinetic energy production, and also controls the spatial distribution of the turbulent flux distribution, which is frontolytic for the equatorial front. So I didn't detail this diabatic branch because it is not preponderant in the total mechanisms. So the most important component is a dynamic component, which is the convergence between the south equatorial and the Guinea current, which is highly frontogenetic and prevails over the diabatic and frontolytic process. So this dynamical frontogenesis influences the monsoon flux, and particularly the monsoon onset, which feed back on the wind energy flux, and so on. So now I would like to present you the interaction between the tropical instability wave with the wind, because this interaction produces a negative PV and strong destratification and the formation of tropical instability vortices. So this figure superimposes, give a view of the potential vorticity in color, and it is superimposed with isopycnals, where we can see the equatorial front. So the alternance of negative and positive pattern along the front correspond to area where the vertical shear current prevails over the vertical component of the potential vorticity, which is associated with vertical stratification. So, in order to understand the presence of negative PV along the front, so we have to look at the sources of PV destruction. For that, we have to consider the PV equation, which is controlled by three terms. The frictional term, which involves the surface current and the surface wind stress, but also the vertical shear of the horizontal current and the vertical divergence of the momentum flux. The diabatic term, which involves the surface buoyancy flux and its vertical divergence, and also the vertical vorticity, and finally, an advective term. So the PV destruction is obtained when the wind is oriented down front, and when the surface buoyancy flux is negative, so when the ocean loses energy to the atmosphere. So the diagnosis of the frictional forcing shows on the top figure, shows that the front and wind interaction, or AD and wind interaction, will explain the negative PV structure along the front in the bottom figure. So now if you look the vertical section across the tropical instability wave materialized by this white line, we see that in this vertical section, that the negative PV present in subsurface and resulting from the AD and surface wind interaction, this PV, this negative PV subduct down to the mixed layer depth, materialized by this black line, to form an intrathermocline bolus of low PV. And this negative bolus of low PV is moved by an anticyclonic circulation. And this negative cyclonic circulation is due to the fact that the horizontal component of the potential vorticity at front tilt into the vertical, into negative vorticity outside the front. And such anticyclonic circulation is very stable, and the vortices can travel over long distance while maintaining their properties, the dynamical, physical properties, and also the biogeochemical properties. So the PV destruction by friction is active in some places of the world, and particularly in the Western Mediterranean, where it is active along the Liguro-Provençal current on the north and the Balearic current in the south part of the basin. And this PV destruction is particularly important because it represents 10 to 20% of production of the West Mediterranean deep water. So the frictional PV destruction is also active in the Gulf Stream, and also in the Kuroshio, as you can see on this figure. The color represents the subtropical mud water produced in the southern part of the Kuroshio. And the diagnosis of the frictional component of PV shows that this process is active in a small-scale oceanic structure. So, I suppose that this process is active. So this process is active as soon as there is oceanic front and wind. So I suppose that this process is active everywhere in the ocean. So now I would present you the warm SST which occur in global model in the summer hemisphere. And this problem is due to a misrepresentation of the buoyancy and mechanical balance in the turbulent kinetic energy. This problem is due to the fact that the current jet which occur in subsurface during the general warming is not represented at all in global model and also in regional model, even at high resolution. Because you can see that this current jet is confined is trapped in the first 15 meters below the surface. And this vertical shear of the current is play an important role in the production of mechanical turbulence. So now, regarding the atmosphere, you see that in the tropical Atlantic, this region is characterized by the presence of intense precipitation associated with the intertropical convergence zone. And this precipitation are connected to the intense vertical velocity, to the upward motion in this region, as you can see on the top left figure. And the two other figures represent the buoyancy and the Ekman component of the vertical velocity. I show you this component of vertical velocity because they are connected to the surface condition, namely the SST, the surface current, and the surface wave. And you can see that the buoyancy W component on the top right is positive in the convergence zone and negative above the cold zone. So when including the current and the waves into the computation of the momentum and its surface fluxes, we modify the component of vertical velocity associated with the buoyancy and the Ekman component. And finally, you obtain a spatial distribution of the precipitation, very different, and these differences reach 200 millimeters per month, as you can see on this figure. So the surface condition strongly impact also the dynamic and the thermodynamic of the atmosphere. So now we are working on the URAC experiment, which took place in the Barbados during January and February 2020. And on the left figure, I present you the differences of SST between ECMWF and NEMO. And superimposed to these differences, you have the wind, the surface wind anomaly, and you simulated by the meso-NH model at kilometer scale, kilometer resolution. And you can see that these anomalies are quite strong because they can reach 5 meters per second. But the most important is the shifting of the convergence and the divergence zone, which strongly impact all the atmospheric column. And in particular, we can see on the right the difference in the precipitating water associated with this difference of SST, which are really quite important and control the spatial distribution of cloud, of atmosphere, of boundary layer clouds. Well, to conclude, so my conclusion is finally a list of requirements. So we have seen that the wind energy flux is a parameter much more relevant than the wind stress to control the vertical mixing, because the WAF is a coupled ocean-atmosphere coupling, because it involves the surface current and the surface wind stress. So first requirements are measurement of surface current and surface wind stress, or directly the wind energy flux possible. So also we have seen that PV destruction by friction is a source of destratification at front and produce modal water in the ocean. And also we have seen that the warm SST bias result of misrepresentation of the vertical shear current in subsurface and the vertical divergence of the momentum flux. So second requirements are the vertical shear of current and the vertical divergence and the momentum flux possible at the scale of the Rossby deformation radius. And then I didn't speak about the PV forcing, the diabatic PV forcing, which involves the surface buoyancy flux and its divergence and also the vorticity. So is it possible to have a measure of the surface buoyancy flux and the vorticity at the surface? And finally, we have seen the surface current and waves have a significant impact on the precipitation in the tropical Atlantic, and this shows that surface conditions strongly impact the dynamic and the thermodynamic of the atmosphere, not only on the boundary layer, but also on the total column of the atmosphere. So thank you for your attention, and we can start the discussion.
Thank you very much for this great talk. Questions? Well, maybe to get things started, I want to ask just a really basic question. In your final slide, or slide 27, I guess, you showed differences between NEMO and ECMWF.
This one?
Yeah, what's the difference between the two? What's responsible for the differences that you see here?
So the differences. So I performed two simulations with Meteo and Ash.
Mm-hmm.
One with SST provided by ECMWF.
Okay.
At I think at 10 kilometers resolution, and the second one is SST provided by Mercator. It's an operational product from Mercator. And I did two simulations with these two products, and I did the difference, and you can see the difference.
So, and then what characterizes the differences in the SSTs? Is it resolution mostly, or is one more responsive to the dynamics than the other?
So the difference in SST is come from the, I think the resolution, but also so the dynamics of the ocean model in Mercator, and also the data assimilated in Mercator, the difference of data assimilated in Mercator and ECMWF. So you see the presence of eddies along in the north equatorial, the north current along the north equatorial current along Brazil, or the Brazilian current, I think it's we call that. So you see you see in NEMO, in NEMO you have the presence of eddies which doesn't exist in the ECMWF.
Okay.
And such vortex, such eddies induce impact the atmospheric circulation in the boundary layer. And not only in the boundary layer, because on the right you have the precipitating water, which is integrated over the whole column.
That's a really striking difference. Other questions? Yeah, Stefan.
This may be a very naive question, but you talked about with the wind energy forcing influencing W, and it wasn't clear to me if you're talking about a direct mechanism or a mixing mechanism. Your conclusion said mixing, but before that it was more in terms of band of mixed layer depth. So I wasn't quite sure what the dynamical mechanism is, unless I'm missing something obvious.
This is this slide, and you talk about this slide. So
well, and the conclusion slide, that's right. Yeah.
Yeah, yes, but there is yes. So the wind energy flux act on the divergence of the current. So you can see that there is two steps. The first step is the preconditioning of the mixed layer. So the precondition consists in adjusting the mixed layer depth and produce divergence in the current. So the divergence of the current induces vertical velocity. This vertical velocity, it is purely mechanical. There is no mixing at this step. the divergence adjusts the mixed layer. So when the mixed layer shallow, it increase the turbulence in the mixed layer because the inertia of the mixed layer is weak, because it is more reactive to the surface wind stress. I don't know if I'm clear, but there is a preconditioning step, and after which trigger turbulence or not.
I think I see the right-hand side of the page. I'm not necessarily understanding what the preconditioning means. That's all. But maybe that's my problem.
The preconditioning is to adapt the deep layer depth. When you have upwelling, you shallow the mixed layer. So when you have shallow deep layer or shallow mixed layer, the mixed layer is much more reactive.
I think I can see that. I'm not quite sure what Tor.u, why that does that, but maybe we should move on. Thank you.
If I can ask a question that sort of follows up on that, I'm curious what, when you're looking at W here, what depth W are you envisioning? Is this coming from W right at the surface or W somewhere in the middle of the mixed layer?
No, it's a mixed layer base.
So, and do you think that that can be diagnosed from divergence at the surface?
I did diagnose the divergence at the surface, but directly the vertical velocity at the mixed layer base. But probably there is similarities between the two signals, I think.
Well, I'm wondering if we might go back to your conclusion slide. You listed a really extensive number of variables that should be measured. And I think that comes from probably the stream proposal, which was envisioning more variables than the winds and currents mission objectives that have been discussed at the moment with the NASA-CNES collaboration. So I think that Stream had a capability had multiple sensors and had a capability to say something about vertical shear. And we're probably looking more at just U and tau.
At the surface.
At the surface, yeah.
And the
so
divergence
is the question, is that a real handicap? Are we missing something critical that that would be a challenge or that would curtail what could be done in a
so the vertical shear will be not are not possible to be measured.
Fabrice or Ernesto might speak to that. But
yeah, I don't think we're going to look at vertical shear with Wacom. And Stream also was just a very tiny spot with the optical sensor. But yeah, I think that's yeah, difficult.
No, but only the surface parameter, that's very good. But is it possible to have also directly the wind work at the surface or not?
Well, I think that's one of the most exciting questions. Wind work, yeah, the idea is to measure wind stress and surface velocity. So that lets you compute the dot product.
Yes.
And that sounds like wind work. But we talked to people who are doing analyses of models. Marflexis did one, and there have been some other studies where people have argued that much of that wind work that you would measure right at the surface is not the wind work that drives the ocean interior. And so then there's a question of what does U dot tau at the surface mean exactly? And I think it's a very rich and complicated question, a subject for a lot of discussion, and people may want to chime in on this. So, and you may have clear opinions on this as well. I can see that
So
nobody
for
wants.
the
Go ahead.
for the vertical shear, we can do a hypothesis about the vertical distribution.
Mhm.
I think. Well, I have no solution now, but we can think about that.
Yeah, I think with the U and tau, there's a lot that can be diagnosed. And as a constraint on an assimilating model, it really puts a strong constraint on what has to happen in the upper ocean.
Also, we have seen in another study that the wind work or the wind energy flux is highly impacted when the surface current is included in the surface wind stress. So when you do the scalar product U tau, when tau is include the surface wind stress, the wind stress is significantly decreased, and it can impact after the dynamics of the ocean. Also,
Yeah, I was going to ask you about that. Because you talked about the interactions of tropical instability waves with wind, and you talked in the Western Mediterranean about PV destruction over fronts. Yeah. And
yes.
There's a hypothesis that people have put forward about eddy killing, winds influencing eddies. I think Lionel Renaud is going to talk about something related to that in a few weeks' time. And I wondered if the mechanism you were looking at was linked to this eddy killing hypothesis at all. So maybe, I don't know if you have an opinion on that. Well, while we ponder, Jacob, you have your hand up?
Yeah, hi. I don't want to interrupt this thread, but I did have a question about the PV discussion. So
yeah, go ahead.
Okay. Yeah, so we looked at the frictional PV flux for the 18-degree water in a model and came to the conclusion that the direct sort of wind force part didn't actually matter for mode water formation, because obviously you have regions of very strong PV destruction, but also you have compensating PV injection. And so the piece that came out in that work suggested that actually the frictional part that had an integrated effect was from the so-called turbulent thermal wind balance or mixing of geostrophic momentum. And the scaling for that would suggest that it's inversely proportional to F relative to the wind force part. So I was surprised in your equatorial fronts that it seemed like dominated by wind-driven PV destruction. So I've been trying to sort of sort out what seems like a surprising result relative to our mid-latitude finding. And so I guess a question is whether you've looked at the time dependence. I'm sort of wondering whether, because these are fronts that are actively undergoing frontogenesis, whether the sort of turbulent thermal wind balance, which involves mixing of geostrophic momentum, that the inertial time scale is so long and you're undergoing frontogenesis, does this explain it? That is there not an established geostrophic flow to be mixed away at these fronts? In which case you might expect that maybe the strength of your PV destruction would lessen as you sort of moved out of the most active frontogenesis phase.
Yes, you are surprised by the intensity of the PV destruction at front, if I well understood.
Yeah, the equatorial front, just because I would have expected that the sort of TTW mechanism would compensate a lot of this at low latitude.
Yes, but probably you were right, but because this diagnosis is a snapshot, so it's not really integrated over a long time. So probably over a long time, positive and negative PV compensate, and finally we don't have I don't know, production of much low PV in subsurface. But
Okay.
so I distinguish this part from the frontogenesis mechanisms processes. So it was this was two different studies, but the frictional forcing in the equatorial region was not really detailed. I detailed the PV destruction by frictional forcing in the Western Mediterranean. So we study in detail this aspect in the Mediterranean, but not in the equatorial. But I did the test in the equatorial region, and I found this figure, and I was so surprised to see that the strong signal along the front. But I should integrate that over a long time to see if there is no compensation. Or
Yeah, no, it's just intriguing, I guess, that it could be. I could imagine it being either the time dependence of the frontogenesis or the low latitude that sort of breaks down some of the TTW assumptions that that would suggest compensation. So, but it makes sense. Thanks.
Mm-hmm. Yes. Mm-hmm.
Mame, do you want to go ahead?
It's more like a basic question, but I think I missed it at the beginning. So the wind energy flux is a scalar, as far as I understand.
Sorry, the wind energy flux?
That's a scalar, right? It's not a vector.
And this figure here, the scale is here.
No, so if wind work is the dot product of vectors, but if you say that the wind energy flux might be better, it's a scalar, so you're missing the directional information there, and I just wonder how this compares, because it's an energy flux, right? That doesn't have a direction.
No, this is a scalar.
Yeah. Okay.
Yes. This is a scalar because it's a product, a scalar product between two vectors.
Oh, I see. It's the result of them. Okay, so I missed that.
So excuse me, I go to the right slide. Yes, here you have WEF equal.
Oh, okay.
Chose scalar U. And this is a surface boundary condition. But if you look at the kinetic energy equation just above here, you in subsurface, in the vertical, you have also this term, but the divergence of this term is included at every level in the ocean. But WEF is only the surface boundary condition. So we have in the kinetic energy equation, we have to take into account the vertical divergence of this term.
Oh, I see. Okay, so yeah, okay, I have to think about it more. I just was confused, but that, yeah, I just missed that or forgot that part. Thanks.
Okay.
Are there other questions?
While we're on this topic, just to clarify, what is the surface velocity in this calculation? What level is it? And what is the resolution in the vertical of the model near the surface?
It depends. So in this study, typically in this study, it was 10 kilometers for the ocean. So U was at 10 kilometers of resolution. And the surface wind stress, so I don't remember.
So I'm also asking about the vertical grid near the surface in the ocean model. Is this a velocity averaged over, say, a 5 meter deep surface grid cell or a 1 meter deep?
No, yes, it is the first grid model. It's 1 meter.
Great,
below the surface. The first grid point is 1 meter below the surface. So yes, it's not really the surface current. It's 1 meter below the surface.
Well, that could be pretty close to what the Doppler scatterometry is actually going to measure. I don't know if possibly Ernesto has a latest estimate of what the effective vertical penetration depth of the instrument is.
Mm-hmm.
Yeah, Roger. From what we have seen in comparisons against bottom-mounted ADCPs and HF radars, I think we reflect a 1 meter, roughly a 1 meter surface current.
The first measurement is 1 meter.
No, let me clarify that just a little bit.
Effectively integrated over that 1 meter.
When integrated, I'll say. Okay.
Yeah. The radar doesn't penetrate the surface at all. So this is the so it has no penetration depth. Just want to clarify that. It's the inferred current depth based on the measurements that we collect from that.
That's correct. So the mechanism is that we're really measuring capillary waves are vectored by gravity waves. They're also vectored by the current. And we need to subtract a gravity wave contribution. And basically we have an empirical training model that we have trained using an ADCP whose surface or nearest surface estimate we use as the training data set. We've also used HF radars, and we've also used optical estimates from dispersion relationship of gravity waves. Those both are sensitive to basically the top meter or so of the surface, depending exactly on which wavelength you're looking at. But the agreement that we have right now is with, after training, is with that top meter velocity.
Ernesto, can you hear me?
Yes.
Sorry, I'm having some issue with my webcam, so I was not exactly sure. I thought we were getting a little bit of biases with Doppler scat and Doppler.
Yeah, so I think it's one of the very interesting things. It's still ongoing work, Luke. But the ADCP and the Doppler, which is a recent measurement that Luke has made, don't seem to agree exactly.
Okay.
And we're trying to understand exactly what the differences are. But I think it's fair to say that whatever the current that we're measuring is not the capillary waves, but is more an integrated current over the top layer, so top meter. So we need to understand those differences. But again, this is an empirical relationship that we're building over time, including in the S mode data. So the hope is that as we build that empirical relationship, we'll be able to train it to roughly meter depth currents.
That makes sense, and we have a pretty good handle on with Doppler on the depth penetration that we can get, so that will be useful. I will be very wary though of using ADCP derived currents at 1 meter depth, because that's not something you can really get.
Is the top layer, the last spin, is 1 to 2 meters is what the estimate was.
Well,
but,
yeah.
So there are surface wave effects and so on.
Yeah, there's a bunch of stuff. As you get closer to the surface, it gets a little trickier. But we can talk about it offline.
Sure. I think that this is a fairly new measurement, and there's a lot of training going on. Luckily, there's a very extensive campaign during the S-mode campaign where we're comparing against Doppler, which is an optical instrument that Luke has. Also against downward looking ADCPs of various sorts. I don't know that I have the answer right now exactly what it is, but I think that we're working our way to that answer so that by the time emission happens, it'll be fairly mature. The ESMO campaign has had one campaign, and we're heading towards 2 extensive campaigns where we'll be refining this answer.
Yeah, and I agree with that completely, Ernesto. I mean, I think we have the right, ESMO is really going to be able to nail this down, which is great.
Any other questions or discussion points for today? If not, thanks Hervé for a really interesting, provocative talk and lots of great examples. And thanks everybody for contributing. I see Fabrice has his hand up, so.
Yeah, just one last question on that last bullet item. I was most interested in Hervé. So you talking about the rain impact in. Can you elaborate a bit more? Maybe send us some nice references about that. That could be very helpful for showing the importance of surface currents in the impact on weather and what you actually mean by that.
Here, this slide. So.
Well, no, the really. Yeah, okay, maybe that.
This is a difference of precipitation. So we did 2 simulation with Meso-NH model, so in this area. And so typically you have this distribution of precipitation in the tropical Atlantic. So it is a convergence zone. And we did 1 simulation with fluxes which did not take into account surface current and waves. Okay, so this is a reference. This is a control simulation. And after we did the same simulation, but including the wave, the surface current and the surface wave providing by the MF1 model. So it is a Lotfi-Auf.
Okay, so that will be changing the flux, the RC fluxes.
Yes, provided the surface waves. So we included this this parameter into the surface fluxes parameterization, and we did we integrated the simulation, and the difference in the precipitation is here in this on this slide, and the accumulated precipitation reach 800 millimeters a month, and you have these differences which reach 200 millimeters a month.
Okay, thanks.
Well, thank you. Thanks to everybody for participating.
So thank you to inviting me.
And the next webinar will be Hector Torres presenting next Tuesday. So we'll see everybody then.